Me
Thank
introduce
you.
you first. Yeah. Hello, everybody. Welcome. Today we are very happy to have Ibrahima Bah, who is going to tell us about the geometry of decoupling fields.
Okay. Very good. Thank you, Inaki. It's great to be here among friends. So I was told this is supposed to be more of an informal discussion. So what that means, please feel free to unmute yourself, ask questions, and if something isn't clear, I'll be happy to try to clarify. Okay, good. So I will, oh, please come on. Okay. So today I will tell you about basically some work that I've done with Federico, who's at Oxford, who will be at Durham, and Enoch and Peter are graduate students at Hopkins, who are both great. So you should look out for them in the future. Okay, so this is based on two papers that appeared in November and December last year. And to sort of put things in context, is when we think about RG flow, we know that anomalies are very powerful in constraining both RG flow and in constraining IR dynamics. Mostly because anomalies along flows are preserved. They're topological data associated to RG flow. However, often what happens in RG flows is you will get operators hit some unitarity bound, and then they decouple, right? So widely, this is called, in many cases, things like accidental symmetries. And decoupled operators, even though they're free, they can contribute to anomalies. So even though anomaly is a constant of RG flows, if you have operators that decouple, they can take away some of the anomalies. So if you care about understanding some CFT, some interacting CFT in the IR, then you need to be able to understand decoupled fields when they happen and how to account for them appropriately. So to this end, what you generically expect in an RG flow is you get some, so in this context, I will just talk about supersymmetric conformal field theories. You get some CFT, but you can also expect some free fields, which may or may not carry some of the anomaly that you started with in the UV. So in the context of geometric engineering, where most of us work these days, where we consider, for example, 6D CFTs reduced on some Riemann surface to get some 4D theories, decoupling of these operators are going to be very important. They're going to be very important if I want to do a correct anomaly matching for the 4D CFT. It's even more interesting because in nowadays, when we try to characterize 4D CFTs that appear in geometric engineering of this kind, we think of the anomaly as part of the definition of the theory, right? So this is broadly called non-Lagrangian theories. The anomaly is part of the definition of the theory. So if you can't not appropriately figure out which part has decoupled when these accidental symmetries have come up, then you cannot properly state what the 4D CFT is. So to sort of make it more specific, what we do in such a reduction is we do anomaly matching across dimension, where we take some anomaly 6 form, anomaly polynomial 6 form associated to whatever 4D system is there. And this can be obtained by integrating an anomaly polynomial of the 6D theory, which generically should be expected to decompose into the CFT and then some free components. And you want to know what these free components are to appropriately capture the anomaly for the CFT. Okay. Any questions so far? I'll assume people are familiar with anomaly polynomials. If no one is, please feel free to ask, and I'll be happy to say a bit more.
May I ask you, this formula captures local anomalies. Is there something similar for global anomalies?
Well, as you know, this formula should capture all anomalies, right? It's a question of how careful you want to be in writing down I6 and how careful do you want to be by integrating over sigma.
Yeah, I was wondering, things like the Witten anomaly, as far as I know, the SDU2 anomaly are not associated to an anomaly polynomial, right? Like
Yeah,
the,
it's not associated to an anomaly polynomial, but it's associated to an anomaly theory.
okay, so there will be some
Right.
formula like
So
this.
in
Yeah. Mhm,
so
okay.
in general, what you should imagine is you have some higher form anomaly, which you call some anomaly theory, but the anomaly theory should be captured by some object which lives in differential cohomology, as you know.
Mhm.
Of course, the polynomial itself, which would be the curvature of such an object, can vanish, but the associated Chern-Simons terms do not have to. And if you appropriately write I8 in appropriate language of differential homology, it should include all of those terms. So as you know
Oh,
very well.
I see what you mean now. Okay.
Yeah.
Mhm, thank you.
Right. So this formula of anomaly matching across dimension, depending on what data you want to extract, it becomes a question, how do you make this? So you have to tell me how you're integrating, you have to tell me how you're writing down I8, and you can keep track of global data if you wish. Okay. There are certain things, however, that this formula may not capture. If you have certain class of accidental symmetries, this formula may not capture it, and we can come back to those points later. In fact, that's related to the fact that you have this I free. Okay, thanks for the question. Good. So these decoupled fields, then these are not mild things, right? So when we think about, for example, n equal to 1 class S, where we take the 6D20 theory, we compactify on a sphere and a torus, there tend to be many decoupled fields, and these will contribute to leading order to the anomaly polynomial. So that you cannot just say they're corrections to your system. And this has been studied by several authors in the past, including myself, which, and some are listed over here. Even in class SK, when you think about reductions with E-type theories, this also have been studied by Shlomo, Gabi, Qumran, and others. And there you could find actually decoupling of fields can contribute to leading order to the anomaly polynomial in lower dimensions. So you cannot just say they're corrections and ignore them. So you need to have a way of doing. Another sort of name, at least in this context, that people might be familiar is the things that are called flipped fields. So I will probably not use that term a lot, but you should think of also flipped fields in this context. Okay, so to sort of study this problem, let me fix a frame and then try to work in that. So I will consider 6D10 AN type theories. These are, more specifically, these are theories that appear in the world volume of taking n M5 brane that is probing some C2 mod ZK singularity in M theory, right? So this is a very precise class of 6D10 theories, which I will want to study. And this is where the class SK sort of constructions also came from. Okay, so what we want to think about in this context is, can we systematically understand and characterize all of these decoupled fields just from the geometric setup? If we're able to do something like that, then we can rely a lot more in anomaly reduction formulas across dimensions and so forth. And again, as I said, these decoupled fields in this context, they usually call flip fields, among other things. And then if you can you give a physical interpretation of what do they do and why they must be there? So first, to remind you about the 6D theory, it has a large global symmetry. There is an SU2R symmetry. It has a U1 and then an SUK times SUK flavor symmetry. So it has a very large flavor symmetry. When we reduce to 4D, we reduce with some choice of background flux, right? There is first a topological twist that we have to do, where we turn on a background flux for the R symmetry on the Riemann surface. This is necessary to preserve SUSY. Then you can get a huge family of theories by turning on background flux on the Riemann surface associated to the flavor symmetries up here, okay? So what this means is when we do the reduction of the theory on the Riemann surface, we take, for example, we consider the background field associated to the U1s in the flavor symmetry, and they will give some 4-dimensional background field, but we also allow a term along the Riemann surface by which we're reducing, and with some choices of fluxes n. So these are called flux parameters, and these flux parameters are going to, there's going to be 2k minus 1 choices coming from the Cartan element of the flavor symmetry here. Okay, so this is a 4D background field, this is a 6D background field, and these are going to be background fluxes that you turn on along the reduction to get a rich variety of 4-dimensional theories. So this specific class had been studied in the past by myself and others in this paper. If you consider the 6D theory, the R symmetry gets reduced to a U1R, and this is due to the topological twist. I will use here R prime to denote just the Cartan element of the SU2R, right? So you can think of this some UV R symmetry. Then you have the U1 flavor symmetry, which just comes along, if not broken. But then because of the flux parameters that I've turned on for the SUK times SUK, then those get broken to their Cartan element. So you have U1 to the K minus 1 symmetry here, and another U1 to the K minus 1 symmetry here. I use the label beta to distinguish the two types of families of U1s that exist. So in 4 dimensions, you get a large landscape of 4D theories that are labeled by the 6D theory, the genus of the surface, and then that are labeled by then 2k minus 1 flux parameters. And this data is what you need to then do the anomaly, the integral of the anomaly polynomial to 4 dimensions. Okay, any questions so far? Okay, cool. So what do you get and what do things look like? So if we, in general, the 6D anomaly polynomial is a function of the Pontryagin on the tangent bundle of the 6D theory. It's a function of the Chern roots of the various flavor symmetries that are present. And if I want to reduce this anomaly polynomial, but when I turn on the fluxes, the Chern roots are exactly the Chern roots of the system you can see as being the background fluxes associated to these symmetries. So I shift the R symmetry in this way. So there is the Chern root of the Cartan element of the U1R seen in 4 dimensions. There's a topological twist, which means that I have to shift it by turning on a V sigma in this way. For the SUK flavor symmetries, I take the Cartan elements, which are labeled by beta, and for each one of them, I shift with some flux parameter along the Riemann surface. And similarly, for the other SU1, which I associated with gamma, we have a sum over the Cartan elements. You have K minus 1 components, and then for each one of them, you get K minus 1 flux parameters that you turn on. So taking this data and then plugging into I8, I can then integrate over the Riemann surface. And when I integrate over the Riemann surface, I get some 6-form anomaly polynomial for the 4D theory, which is going to be a function of the Pontryagin class of the tangent bundle in 4 dimensions. The Chern roots of the various U1s, the U1R symmetry, in this case, it's expressed in terms of what I call the UV U1R symmetry. And then you have the various U1s coming from the breaking of the non-abelian theory. But this, more importantly, is going to depend, will have coefficients, which is the anomaly coefficients, that's going to depend on the choices of all of these flux parameters in my story. Okay, so what sort of a thing do you get? So let me give you a specific example. If you choose, for example, the flux, you just take k equal to 2, so you have SU2 times SU2 non-abelian theory. non-abelian flavor symmetry, and then you turn on. So for each one of those SU2, it gets rank 1. So you turn on flux for each one of those U1s, and let's say we turn on the minimal allowed flux, which is 1. This theory you can study in another way. So there is a proposal of trinions for reductions of this class of theories in 4 dimensions. So you can construct actually a Lagrangian for this case when you put it on the torus. Okay, so this goes to some work by Razamat and Gayotto. And if you consider such a trinions, you can construct an explicit Lagrangian. And actually what you do when you construct such a Lagrangian, you get the n equal to 1 Klebanov-Witten theory here, where you have a SUN gauge group, and then you have some bifundamental matter that goes between them. But you get something extra with it. And this extra bit is exactly reflecting what I was trying to say earlier. What you actually get is the Klebanov-Witten theory coupled to two scalar singlets of the gauge group, which you are called phi beta and phi gamma, right? So I don't get exactly the Klebanov-Witten theory when I construct the theory using the trinion. I get the Klebanov-Witten theory coupled to two scalars, two external scalars. And when I actually compute the anomaly polynomial by the reduction is going to be that of the Klebanov-Witten theory plus contribution coming from these two scalars. So here, these scalars couple in a very particular way to the Klebanov-Witten theory. They couple by shifting the superpotential. They couple to the baryonic operators of the theory. So I have a baryon, which is determinant of Q, where Q is one chiral superfield going here. Then you have another chiral superfield going here. And then these scalar singlets, they couple to these baryons. You can compute explicitly their charges. So if I can write their charges. Go ahead.
Can I ask you the previous? Yeah, no. So in Klebanov-Witten, the baryons are like resolving the singularity, right? So this
good. So we'll come back to this point.
Okay.
Yeah, good. So there's something about the baryon. So when you turn on the baryons, you go into the baryonic branch, and they're associated to. You associate them morally with resolving the singularity, and we'll come back to this point.
Okay, thank you.
Good. So good. So let's just think a little bit more. So about the charges of these fields. I write the charges in terms of the UV R charges. So R prime is the UV R symmetry that I get from the SU2R. So both of these fields have charge 2. Okay. This is consistent with the fact that the chiral superfields that generate the baryons, they are not charged explicitly under that U-R symmetry, so the baryons themselves are not charged under that R symmetry. And these scalar singlets must have R charge 2 because the superpotential must have R charge 2. Similarly, they are charged under some U1 flavor symmetries. These are the baryonic U1s in my system. Those baryonic U1s, basically, the chiral superfields are charged under them, right? There is a Q and a Q twiddle with charge 1 and -1. So then the baryons associated to chiral superfields will have charge n, order n or -n, depending on your choice. So these singlets will have charge. So one of them should be a minus. Let's say this one is a minus. So these chiral superfields, from which we get actually, they have very large flavor charges under these baryonic U1s. So what this means, of course, is that the superpotential operator that is being added is actually an irrelevant operator, right? So as you can see, it's an irrelevant operator because of the baryons here that have very large charges. But even so, what that means then when you go to the very deep IR, this operator drops off, and then when it drops off, you go back to the CFT fixed point. However, the key point here to note is that these operators are coming in along the flow, when I'm going from 6D to 4D, and I cannot ignore them. And in particular, the anomaly polynomials knows exactly about these scalars, and it includes them. Even though they decouple, these scalars are part of they contribute to the anomaly polynomial that I get by simply reducing. And because of these large charges over here, they contribute non-trivially to the anomaly polynomials themselves. They contribute order n cube actually to the anomaly polynomial. So they're highly non-trivial, even in this simple example. So actually, so if you were to, so to be more pedantic about this point, if you were to just take the anomaly polynomial that you would compute in this case, including these scalars, and then you were to, let's say, A maximize, try to compute the central charge, what you would actually get is the central charge that will scale as n to the 3/2, which is very far from what the right answer is, which is n squared, right? So here you could see that this is another way to see that if you don't know what these fields are, then you miss the CFT point completely. You have to subtract them, and when you subtract them appropriately, then you will be able to recover the correct central charge for the theory, for example. So if we continue even in the k = 2 case, and let's say you consider even more generic fluxes in this case, you can rewrite the fluxes as being P plus Q and P minus Q. And what you find in this case, actually, the compactification of the 6D theory via the anomaly polynomial gives you a YPQ theory, right? These are the YPQ theories in 4 dimensions, which have been studied quite a bit, but you don't get exactly YPQ theories. What you get is YPQ theories coupled to many scalar singlets of this kind, many gauge singlets. And for example, you will have order n beta of these singlets. So you have many of them that show up in the low energy. So you get, order n scalar singlets which have large charges under the flavor symmetry, so they contribute highly non-trivially to the anomaly polynomial. And again, in this case, because you have another indirect way of checking what the IR theory should be, you can then subtract off what these things are, and then you can show that actually the theory will flow to this CFT fixed point, okay? And part of the reason why you can sort of independently deduce that these theories in these examples are this is because you're compactifying on a torus, and there are various methods when you compactify on a torus to figure out what the Lagrangian, so there are Lagrangian theories, so you can figure out what the Lagrangian should be, and then from there you can compare the 2 theories and see that you get extra fields, so you know that you should throw away those extra fields because they should decouple in the IR, because they come in with irrelevant operators. But if you consider the general compactification to a Riemann surface, to maybe a surface with punctures and all sorts of things, where you genuinely get non-Lagrangian theories, then the anomaly is the thing that is sort of defining your low energy theory. And you don't know what is the contributions of decoupled scalars. And as we just argued, the contribution of decoupled scalars could be as large as n cubed, and in some cases, even n to the 4th, okay? So this is a rather interesting problem to try to understand how to resolve in a systematic way from geometric engineering. Okay, so before I proceed, any questions? Okay, so you want to try to then compute, for example, this anomaly in a different way. So the 6D10 theory is the world volume theory on a stack of N5 branes that are probing some C2 mod ZK singularity. So what we've just done is we've studied this theory by starting M theory, flowing down to 6D CFT by decoupling gravity. So when you do that, you get the 6D CFT, but then you also get some free tensor and free vector multiplets, which are associated to center of mass modes and other things. And then we took the 6D theory, we have a construction of the anomaly polynomial of the 6D theory, and then we reduce down to 4 dimensions to get an anomaly for the 4D theory down here. Okay, and this is what we just did. And as I've just hopefully convinced you, when you go down this path, there are a lot of decoupled fields that are fairly troublesome, and you want to know how to characterize them. There is another way to get to the 4D theory. Instead of going through the 6D down to 4D, you can just start from M theory and try to go directly to the 4D theory, right? So let's see, can I just take some compactification of M theory and then do a reduction that allows me to go directly to the 4D theory? And if I can do that, then I can have a different computation of the anomaly polynomial. I can compare the two and ask, are they the same? Do they have the same information? And what does the difference include? So we want to figure out how to do the direct reduction of M theory to 4D for the anomaly. So this problem had been studied extensively by me, Federico, Ruben, and Emily Nardoni in a sequence of papers. How do you reduce the M theory? How do you reduce anomaly for CFTs constructed in 5 braids from M theory? And the idea was referred to as an anomaly inflow onto the 5 branes. So we consider we have a stack of 5 branes that is sitting here. There is it's sitting at a tip of a cone, and this cone here is exactly the C2 mod ZK singularity. And what we want to study is if you have these 5 branes, from the point of view of M theory, they serve as a boundary, as a boundary for the space. More in particular, they serve as a boundary of some 5D supergravity theory here. So there is an anomaly inflow that goes from the bulk supergravity onto the branes. And because the theory has to be a consistent theory of quantum gravity, the anomaly inflow tells you that the anomaly of the quantum anomalies for the gauge, for the global symmetry on the branes have to cancel with the classical bulk anomaly for the gauge symmetry, right? So this is a statement of anomaly inflow. The bulk gauge symmetry gets imprinted as a boundary global symmetry. In the presence of the boundary, the bulk gauge symmetry is anomalous. It's classically anomalous, meaning if I look at the effective action and I do a gauge transformation of the effective action in presence of the boundary, there's going to be an anomaly, meaning it's not going to be preserved. But then there are going to be some global anomalies for the symmetry on the branes, and those two must cancel in order for the theory to be consistent. Okay, so the story from an M theory point of view, you have a stack of branes sitting at the tip of the cone of this, and then you want to study this problem, and you want to compute the anomaly directly by an anomaly inflow argument. So for the setup of interest, we have the branes wrapped on some Riemann surface here. So M theory will decompose into R1, 3. This is where the 4D theory lives. There's the Riemann surface wrapped by the brane, and then the transverse direction splits into some R, then there's the C2 mod ZK singularity. If you come in the region near the brane, the M theory background becomes R13, where the field theory lives. Then you have an overall radial direction, which is a radial direction moving away from the branes. And then you have some compact directions, which we call M6 here, okay? Now, M6 has a very particular structure. It's a fibration. It's a fibration of some 4-dimensional space over the Riemann surface. And the structure of this fibration is determined exactly by the topological twist that you needed to make in order to preserve supersymmetry. On the other hand, this M4 has also a particular structure. For the case of interest, since we're working in supergravity, we have to resolve, for example, all singularities. So if you imagine the branes that are sitting there, there's a little group acting on it, which is SO5. That little group has a sphere associated with it. So you can imagine the sphere surrounding the branes in M theory, the 4th sphere. Due to the presence of the orbifold, that 4th sphere becomes an S4 mod zk. There's it's an S4 mod zk. So this M4 that we have here is we take this S4 mod zk, but we consider a resolution of this S4 mod zk because we need to do that in order to use supergravity analysis. Okay, any questions about this slide? Okay, so with this in mind, you can imagine taking M theory supergravity and then reducing it on this M6 spacetime. This will give you some external 5D supergravity for which the branes are going to be some sources for. Okay, and there will be sources sitting at the tip over here. So now to correctly capture the anomaly in this case, the anomaly is going to be the topological sector of this 5D supergravity. If I take the M theory and I reduce it on M6, I get some 5D supergravity, which will have some topological sector. This topological sector is exactly what you get after you do anomaly inflow, right? So this topological sector is what will correctly capture the anomaly polynomial of the theory that lives on the brane. And how this works, we've studied over several papers with Federico, Ruben, and Emily, building on some earlier work by Fried, Moore, Harvey, and Minassian. Okay, and the strategy or the structure of how you compute this is you consider, so since I have 5 branes sitting in M theory, they're going to source the 4-form flux in M theory, and their presence from the point of view of the M theory supergravity is how they source the 4-form flux, and that should also include information about the branes and how they're wrapping various cycles like the Riemann surface. Then, given this 4-form flux near the brane, it has to have some. You can consider some equivariant extension of this, which we call E4. This equivariant extension is with respect to the isometry group of M6, okay? And then once you have this E4, you can compute the anomaly polynomial of the 6D, of the 4-dimensional theory by just integrating what we call some M theory anomaly, right? So you construct an E4, then you integrate it over M6, and then this gives you an anomaly 6 form, which captures the anomaly polynomial of the theory that lives on the brane. So X8 here is just the Pontryagin classes that appear in this M theory Chern-Simons coupling. If you don't know the details, if this did not make sense, it's okay. It's not going to be super relevant, but for the expert in the room, this is how we would compute, for example, the anomaly polynomial for these lower dimensional theories. Any questions?
Yeah.
Go ahead.
So I12 here, how should I interpret it? Is it differential cohomology or is it an ordinary 12 form?
Good. Mm-hmm. So in the context here, I'm just looking at, I'm keeping track of continuous symmetries. So it is a 12 form, but I can promote it to an object in differential cohomology where E4 is a differential character of a specific class. This is a specific differential character. So you have to pick a choice of a differential character for E4, and then you want to push forward on M6 to get the anomaly polynomial.
Oh, very good. Okay, I see. Thank you.
Okay, so this is the same story that you're already familiar with. So far in our work, what we had done is to clearly establish that if I want to know what the anomaly is, I always start with this I12 where I have to construct E4 following G from the flux, right? And then if I want to keep track of global anomalies carefully, and I want to keep track of anomalies associated to, let's say, discrete symmetries from torsion, then I cannot think of E4 and G4 as just being continuous forms. I should think of them as differential cohomology objects, and that has much more data that you can keep track of. But at the end of the day, it's the same object where you would promote I12 as an object, as the curvature of a differential cocycle.
Thank you. I guess the thing I was a little bit confused about, what does equivariance imply here? So why did you say this is the equivariant completion? Why is not just G4 or yeah?
Good. So G4 as given is a form on M6. right? But then M6 is fibered over the external spacetime where the structure group is given by the isometry. So I have to take G4 and I have to extend it to the full spacetime, to the full 11D spacetime. And to do that, I have to do an equivariant completion of G4, and that becomes E4. Or said another way, in physics terms, what I'm doing is I have a four-form flux in M6. I can gauge the isometry of M6 over external spacetime. And when I gauge that isometry, I also have to gauge the four-form flux. Is that better?
A bit. I think I will ask you after the talk, if that's all right.
Okay, good.
Thank you.
Yeah, I can also provide more details.
Thank you.
Okay, so what is the data that allows me then to compute this thing? So let's go back to here. So I started with the S4 mod ZK, and I've resolved the orbifold points. So so S4 mod ZK have two fixed points, right, which are sitting at the north and the south pole of the fourth sphere. So each one of those fixed points locally is R4 mod ZK, so is a Gibbons-Hawking space. So I can resolve each one of those guys by replacing them with a chain of bubbles, right? So this is the same way that I would resolve a given Hawking space. So I resolve them with a chain of bubbles in the north pole, also a chain of bubbles in the south pole, and this is just some interval that interpolates between the two corners of the space. So the topology of M4 is roughly depicted here. So M4, which is S4 mod ZK resolved, is roughly depicted here. So here I have K minus 1 resolved 2 cycles, which is exactly what I would get if I resolve this type of singularity. Okay, so now once I do that, then M4 has non-trivial homology and cohomology groups. So there are some number of 2 cycles. There are 2K minus 1 independent 2 cycles, which are coming from the resolution 2 cycles at the poles. There is an extra one because you have the Riemann surface sigma sitting in M6. You have the Riemann surface sigma. There's an extra one, but that extra one is actually going to mix some components of M4 with sigma G. So there's one more. So then you get 2K minus K minus 1 in the north, K minus 1 in the south, plus one more. It gives you 2K minus 1. And then by Poincare duality, we also have 2K minus 1 4 cycles. And these you can understand by constructing them by taking the 2 cycles we described here. And then for each 2 cycle, you can combine it with the volume of the Riemann surface, and this will give you a 4 form. It will give you a 4 form. It'll give you a 4 cycle from which the volume form of that 4 cycle is given by a 4 form that looks like this. And then on top of this, you have the actual M4 space that's sitting there. So this will give you again 2K minus 1 independent 4 cycles. Any questions? This might be too fast.
So I should think of the other R4 mod ZK at infinity.
Come again?
There are 2 R4 mod ZKs, right? But when we started, there was only a single R4 mod ZK. The other one is coming from infinity?
No, it's not coming from infinity. It's just the fact that if the 5D space is R times C2 mod ZK, right? So you have actually a whole line. So in the 5D, when you do the orbifold in the 5D, you have a line fixed point. But then if you consider the sphere in this 5 dimension, the sphere will intersect at 2 points of that line of fixed points, right? And that's where that is coming from. Yeah, good question. Thank you.
Thank you.
Okay, good. So that is the data that you need. So notice that all that I'm giving you, I could ask about having a local metric describing this. I can pick any local metric as long as it preserves this cohomology. And at the end of the day, the anomaly is just going to care about this topological structure of the space, not so much what the local metric looks like. So to just put a little bit more meat to this game, the 4-form flux near the brain, here it can be expanded as n, where n is the original stack of n branes times the volume of M4. So just think of when I take this R5 without the orbifold, then the flux will have n times the volume of the sphere that surrounds the brane. This is just what this term is. But then for every 4 cycle, I can turn on some flux, some background flux here. For every 4 cycle, I can turn on some background flux. And then for every 2 cycle, I can turn on a flavor U1, right? I can turn on a flavor U1 for every 2 cycle here. So these guys should think of them as background fields that you would associate to the U1 to the K to the 2K minus 1 that you have when you try to reduce the 6D theory, right? So these are background fields for the Cartan elements of the SUK times SUK flavor symmetry. Okay. So you get, so then if I just construct G4 in this way, in general, I have 2K minus 1 flux parameters coming from these guys and that guy. And then I have 2K minus 1 background fields associated to the U1 to the K minus 1 of the SUK. So I should actually be a little bit more precise here by saying this is a subgroup of the U1 times SUK times SUK flavor symmetry here. Okay. Now, with that said, we can go ahead and play the game of equivariant completing G4 here. What this means is that you do an equivariant completion of each one of these forms. So this is the form in the space M6. You gauge the isometry group, and you gauge it in a way that you still recover a closed form in the full 11D spacetime. Okay. If you want more questions on how that works, I'll be happy to discuss it after the talk. So an important map between the analysis in field theory. So in the field theory, what I had is the Chern roots associated to the flavor symmetry. In the geometric construction, what I have is these background fields, and these are the same, right? So these background fields that I would turn on in the north, they map to the Chern roots with the beta U1s, and the soft guys map to the Chern roots of the gamma U1. So you have an explicit map between the field theory and the geometric construction. So now I've given you 2 ways of computing this anomaly for whatever you get at 4D, so we can compare them and see what we get, right? So we have one, which is the anomaly inflow that I get by integrating the M theory anomaly, which is what happens when I think of the 5 branes probing the flux background and computing the anomaly that way. The other way that we also discussed is I get the anomaly by integrating down the anomaly polynomial of the 6D SCFT. So this would be the standard anomaly matching across dimensions. So if you compare these 2 answers, what you get is you get the anomaly of the 6D from inflow is going to be equal to the anomaly of the CFT here. Here you have some contribution coming from decoupled vector multiplets in 6 dimensions. I'll explain more what it means. But then you get an extra piece, which is I3. Okay, and that's important to know that if I compare the inflow anomaly and the field theory anomaly, I do not get they don't match, they don't agree, and they're different by some amount, which I will call I6-free. So to just recap what these different answers are. So in the first case, the way we thought of it, we have M5 that are probing C2 mod ZK. It goes down to giving me, on one hand, a 6D 10 CFT, which is the one that's defined. And then it gives me a free tensor multiplet, which correspond to the center of mass modes of the branes, and also free vector multiplets, which is associated to the fact that I have the orbifold. Okay, so this is free 6D stuff, and then I have 6D 10 theory sitting here. Then I take the 6D 10 theory, I compactify down on a Riemann surface, And when I compactify on a Riemann surface, I get a contribution, which is going to be free fields, which is this contribution here, right? But I get the contribution of the 4D CFT here. Generically, from this computation of the reducing of the 6D10 CFT, I don't know what this contribution is, so I can't really decide what this thing is. So in the other computation, directly from M theory, what I get is a different story. I have 5 branes that are probing in the flux background. This guy splits into 2 ways. I get a contribution, which is the CFT, but then I also get another contribution, which is the free tensor and the free vector reduced on sigma g. So this term here is basically the same as taking this term and reducing it down on the Riemann surface. Okay, so this is just the stuff that decoupled at the level of 6D. That stuff should still decouple. It should not recouple with the theory. So this stuff here does reappear even over here, but then I know to expect it. I know I should get a center of mass mode, and I know I should get some vectors decouple coming from the orbifold. So this is known data. So I know what they are, and I can reduce it on the Riemann surface, and I can subtract it. And what this means then, the direct reduction from M theory in the flux background then correctly captures the anomaly of the 4D CFT here, okay? Whereas the reduction of the 6D theory doesn't have the 4D CFT plus some extra stuff. This also gives me an idea, gives me a perspective on how I should understand what this free stuff should be compared to this guy, right? So the computation directly from M theory then always gives you the correct CFT answer. Yeah. So now let's talk about what the free part looks like. Question?
Do you know that there aren't free fields in the direct reduction?
Sorry, come again. Repeat. You sort of broke up.
Yeah. How do you know that there aren't free fields in the direct reduction from M theory?
How do I know that there aren't free fields in the direct reduction?
Mm-hmm.
So this would be extra free fields that would appear here and here, right, on both sides.
I see. Okay.
Right. So they would show up at both sides, but in the M theory construction, we know with decoupling gravity, and the only free fields that should appear there, we can know from the mechanics as coming from the decoupled center of mass mode. So when you reduce the M theory, you do expect to get the anomaly of the CFT. In fact, that's how you also compute the 6D, where you just do inflow to the 6D theory to 6D, then you recover this, and you know you have to subtract this, and this is how you know what the anomaly of the 6D theory is also. Okay, so the reduction of the M theory you understand and you trust, but that's a very good question. Or said another way, there's a very holographic perspective you could also have on this. The anomaly that you get by reducing M theory is that you could imagine as being the same anomaly that you would get if you go to the near horizon of the branes. But if you go to the near horizon of the branes, you know you can expect some weakly coupled ADS theory, but that weakly coupled ADS theory is going to be dual to a theory which have a unique stress tensor, right? So it's a single block of an interacting theory, not sum of components. There's a holographic intuition of why you expect that to give you this, the actual interacting theory.
Thank you.
Yeah. But that's a quite excellent question, which deserves a bit more thought. Okay, so what does the free part look like? So you can compute the free part. The free part will have two contributions. The first contribution is going to be an anomaly of a bunch of free chiral fields. So I have free chiral fields here labeled with I and J. So I and J here are labels of the SUK symmetry, okay? And I sum over them. I sum over them with some multiplicity here, and that multiplicity is the flux parameter n. Okay, so I get so this is a matrix of scalars that I have here, and that matrix of scalars are going to have some multiplicity, which is given as it turns out, by the flux parameters here. So to get this answer, right, it required actually a significant work of taking what you would get from the field theory and then actually pulling out this piece. It's sort of actually miraculous that it worked, and this was due to Federico, who figured out that you actually can reorganize the difference of here and here as a sum of some free fields, where that sum has a very particular structure, and that sum is going to be equal to taking the anomaly of a collection of free fields here with some weight, where the weight is a multiplicity factor. You get something like this both in the North Pole, and you get something like that also in the South Pole. So you can look at the charges of these fields, of these free fields, and see what they are. Since they are free, they have R charge 2. But then you can look at their charges under the baryonic U1. So the ones in the North Pole have the matrices in the matrix of scalars in the North Pole have charges which are n. So this is important, times the Cartan matrix of SUK. So it turns out that's what the charge is going to be. And those in the South Pole have charge minus n times the Cartan matrix of the SUK in the South Pole. Okay. And then each one of these families have some multiplicities, which is scaling with the flux n. So in the anomaly polynomial, T's give you some rather large correction to the anomaly. They actually give you an n to the 4th correction to the anomaly. So in fact, naively, if you just write down the anomaly polynomial, the decoupled free stuff that I should remove seems to even dominate the contribution to the anomaly polynomial. Okay, but somehow by comparing the inflow answer with the free vector that we know it should be there, comparing basically this side with that side, we have the difference, and then after some miracle, this difference organizes in terms of free fields with some multiplicity that we know that we can obtain explicitly. Okay, any questions about this? Okay, so this is punchline 1. Then you can ask, where are these free fields coming from, right? So far we've compared 2 anomalies. We looked at difference. The difference gets organized in this rather highly intricate, non-trivial thing. So it should have some clear geometric origin. So where are they coming from? So now we're going to do a different sort of computation, and this will provide an answer, which is also related to a question that Inaki was asking earlier. Is if we go back to this space M4 where we resolve these cycles, we can consider a class of operators which exist in the 4-dimensional theory, right? We can consider a class of operators which correspond to taking M2 branes, and for every M2 brane, for every 2 cycle, I wrap an M2 brane on it, right? So that is an operator that corresponds to some chiral operator for the 4-dimensional theory. Okay, so it's a protected operator. So if I wrap an M2 brane on each cycle, I get a protected operator. And in general, you will get 2k minus 1 of them because you have 2k minus 1 2 cycles. Now these M2 branes are going to be operators in R13, so they just sit at a point. But more importantly, they also sit at a point on the Riemann surface. So you can take each one of these M2 branes, you can then calculate what is the charge of those M2 branes are under the symmetry of the problem. So I table it here. So I have a class of M2 branes that are sitting in the North Pole, and I have a class that's sitting in the South Pole. So they form a matrix Bij, because if I take an M2 brane, I can wrap it, I can take any linear combination of cycles and I can wrap an M2 brane on it. So you get a matrix of M2 branes actually by just corresponding to taking an M2 brane that wraps cycle I and then cycle J. Okay, so I can then compute the charges by simply writing down the effective action of the M2 brane and then reducing on the external spacetime. Then you can compute the charges of what those M2 brane operators are. And they have, for example, R charge 0. But if you look at their U1, their charges under these things that I call the baryonic U1s, not by accident, the North Pole ones have charge minus n times the Cartan matrix, whereas the South Pole have plus n times the Cartan matrix. These charges are exactly commensurate with the charges of the decoupled scalars that we observe when we compare the two anomaly polynomials. And in particular, what it means is that the scalars here can combine with the M2 brane operators, which are often called baryonic operators, to make superpotential terms, right? Because it has R charge 2, so and the M2 brane operators have R charge 0. So I have this object here, which is a superpotential term, and then I have another one of it here, which is a superpotential term. Okay, so you find that for every M2 brane, you can associate a class of these decoupled scalars, but the decoupled scalars come with some multiplicity. So what does it mean to take a single brane and associate it with many set of scalars? In fact, this counting is also should work, because there's also a degeneracy for each one of these M2 branes. And this degeneracy goes back to some rather physics that you learn early on in your career. If you think about the M2 brane that's sitting on the Riemann surface, it's a point on the Riemann surface. That's nice. So what that tells you then, if you can think of it as a point particle that's sitting on this Riemann surface here. So then what this M2 brane is from the point of view of the effective theory on the Riemann surface is a point particle with some flux going through it, right? It's a point particle with n units of flux going through it. And then Landau long ago told us that if I have a particle in a magnetic field background, there is a degeneracy for the ground state. The ground state is degenerate exactly given by the number of flux units. So if you consider an M2 brane sitting on the Riemann surface which has a non-trivial flux background, then the quantization conditions for such a M2 brane tells you that the ground state is degenerate, and it's degenerate exactly given by the number of flux value here. And then if you look at the degeneracy number, it's exactly the degeneracy that you get for these fields that we observe were in the difference of the anomaly polynomial. So indeed, the gauge singlets that we observe in the anomaly, in the difference of anomalies, map 1-to-1 to a set of M2 brane operators in the construction from the geometry. Okay, so what is now then the physical interpretation of what's going on? So let's talk about some physics here. So the physical interpretation is as follows. So the presence, the M2 branes, oh, I should use B, right? So the physical interpretation is that you have your M2 brane operators, they can combine with the scalars to make a gauge, to make a superpotential term. So these are irrelevant operators. Then you can think of this that as you're doing the RG flow, so as you're going from the UV to the IR, here, somewhere here, as you get very close to the CFT points, there are going to be bunch of singlets that are decoupling. But in this region here, these singlets, they're coupling, they're exactly coupled to the baryonic operators, and they are, you can think of them as the leading irrelevant operators if I try to flow back up. So if I try to sort of flow back up, you can ask, what are the leading irrelevant operators that I would hit? Those leading irrelevant operators are exactly going to be these guys, right? So that's the physical interpretation of why I keep seeing them when I try to write down a Lagrangian for the 6D reduction on the Riemann surface. On the other hand, from this point of view, since they appear in the superpotential in this way, and the scalars do not couple to anything else in the theory, this actually does something else fun. And what it does is that it has an F term, right? I can compute the F terms for these scalars. And what those F terms do, they will set these baryonic operators to 0. So these superpotential terms, what they do, they are projecting out the baryonic operators along the flow, right? So these baryonic operators must be there. So what is happening is that in the 4-dimensional theory, the baryonic operators must be there. They parameterize the baryonic branch of the theory. However, the fact that this is the leading irrelevant deformation means that if I go back to the 6D theory, there is no analog of these baryonic operators. They shouldn't be there. There's no analog with them. This has a very clear physical interpretation, which is that if you go back to the 6D in the construction of the 6D theory by just decoupling gravity in M theory, you could have blow-up modes, which would blow up the 2 cycles from which I'm putting the brain. Okay, so in the 6D theory, there's actually no operator in the 6D that does the blow-up mode while preserving the Lorentz symmetry. There are Fi terms that you can turn on, and so the Fi term corresponds to blowing up 2 cycles, but those Fi terms, they break the Lorentz symmetry, so you don't include them in the spectrum of operators in the 6D. Whereas when you go down to 4D, you preserve a lower Lorentz symmetry. These blow-up modes are actually part of the theory. They parameterize the baryonic branch of the theory, so they must be part of this. So this gives you now a clear interpretation of what these singlets or flipped fields are doing. They're basically interpolating between keeping some operators in the IR versus throwing away those operators in the UV. So the blow-up modes aren't present in the UV, but they are in the IR as being the baryonic operators. So the singlet fields phi, they just serve as something to interpolate from the UV to the IR for this rather very specific physical phenomena. So the flip fields, we should think of them as interpolating between these 2 rather important features and aspects of these both 6D and 4D theory. Okay, so this now gives you a systematic way to access and study flipped fields or decoupled fields in geometric engineering. And this sort of approach and idea is widely generalizable and also applicable to many other contexts that many of us study and are interesting. So there are many other contexts to explore these ideas, and they should teach us quite a bit. So I will stop here. Thank you.
Thank you very much for the great talk. Right, any questions or comments?
So this was a lot. I can go back to various corners and put it in more detail if people want.
Yeah, that'd be great. I have already asked many questions, so I'm refraining myself from asking right now.
Okay.
If anybody has any other question, please go ahead. Right. If not, I suggest that we thank Ibu again and stop the recording. Thanks.